Okay, today I want to show you how to measure the in situ stress after the brief introduction about the importance of stress and the influential factors of the in situ stress. Again, you have 9 components for stress tensors. So how to determine the stress? When you consider how to determine the in situ stress, you need to understand one critical issues. How to get there? If you want to measure the in situ stress at 1,000 meters in depth, then you need to think about how to get there. 1,000 meters. Okay, it's 1 kilometer, right? So how to get there? So usually we were trying to use borehole. It will be one of the possibilities. Okay, so we will have the hydraulic method where you put the borehole into the subground and you try to provide a pressure to make the rock better. If you understand the influence of the rock failure versus in situ stress, then you can try to use this information to evaluate. Do you still remember here? I'm talking about 2P and the strength of rocks. Very simple way. If you know the strength of the rock and you make the rock better, and you can evaluate the possible in situ stress. Can you connect this? So this will be related to the hydraulic method. So they will try to measure the stress at the bed. And we will have another 2 approaches. Idea. The one idea will related to the compensate stress. We trying to release a stress. And the rock will deform. Okay? We only know the rock deform. And we try to apply a stress to make the rock going back to the original position. So it means I compensate the stress. Before I remove the stress, I don't know how much the stress is. But I release the stress, the rock will deform. And I apply a stress to make the deformation go back to the original condition. So I will think about, okay, the stress I apply is a compensated stress for the removed one. So I can use this to evaluate the stress. Can you understand the idea? And the third one will be the relief method. We will not really try to compensate the stress. When I try to remove the stress, the rock will deform. If we know the deformation, the relation between the deformation of rock versus stress, then I can evaluate the stress via the strain, where I relieve the stress. This will be the 3 basic ideas for in situ stress rating. Okay? Stress will be an invisible thing. Can you really see the stress? No way, it's impossible. But usually you can see the result of the stress. Okay? For example, if you hit me, I will have a broken rock. So I will have some purple color here. So this will be the result of the stress. But you cannot see the stress. So for the measurement of stress, we usually try to use the strength or the deformation of displacement and try to infer the in situ stress. And the other probability, like I introduced you, will be the observation of failure of rock. The failure of rock will be another response or another result of stress, right? If you have very large deviatory stress, then the rock will fail. If you can make the rock failure, then you can go back to evaluate the situ stress. Okay, I will talk to you later about these three methods, but I want to mention to you one important thing. The flat jack method, you need to cut a slot and try to put some hydraulic pump to apply a load to push the rod slot go back to the original condition. So how can you do this at the 1,000 meters depth? And the relief method, you will try to drilling a hole. You will try to drilling a hole and put some strain gauge or some markers of the displacement and a wall, some wall. And you will try to measure the displacement from the marks or the strain gauges. After you relieve the stress, you will try to cut the rock, take a sample out, make it free movement. Okay? So you need to do a lot of very precise work on this. So can you do it at the ground surface for 1,000 meters in depth? It's nearly impossible. So for these two methods, you need to have some ethics, or you need to have some shape to do this. Usually, for tunnel, you want to investigate the geological condition. You will have some ethics for exploration. You will have some ethics in advance, and some geologists going into the ethics and trying to do some geological work. You will have some ethics. Or sometimes you will have some shape. The shape will be very useful. When you have a mountain like this, when you have a mountain like this, and you want to drill in a tunnel like this, so you can only drill in a tunnel from here and here. If you have a shape in this direction, then you will have 4 phases to start your work. You can drill in a tunnel from here, from here, from here, and from here. So the time of the construction will shorten half. Okay, so you will have the shape like this. Or sometimes, as I told you, you will have some shape, some edits like this. You will have edits here. So some of the methods should be conducted in the shape or in the edits. If you don't have the shape and the edits, you cannot do it measurement via this method. That is the reason why I want to mention to you one important thing. How can you get there to make your measurement? Okay? So I will stop here and see you next week. Test. I will start from the hydraulic fracture method. So this method need a borehole. So if we want to measure the stress at a great depth, like 1 kilometer. So you can drilling a borehole to the depth where you want to measure the stress. And you will try to make the borehole break. So how to make the borehole break? You will try to seal the borehole in two locations. And we will try to inject the water or fluid into the section. So you will try to use the so-called packer, like a tire, like a rubber, and you can inject the air into the rubber. Then the rubber will expand. And when it expands, then you can try to make this segment isolate. You can have a packer here, and you have a packer here. Then trying to expand it to tightly contact with the borehole. Then you can inject the water into this segment. Then the water cannot escape to the upper part and to the lower part because you have the packer there, expanded packer. So this will be the hydraulic fracture. So it will be an illustration like this. If we cut a cross section here, then you will have a cross section like this. This will not be a tunnel. This will be a borehole. So you see the borehole in the top view. Then you will have a cross section. You apply a pressure within this segment. Then you will have an in situ stress field like this. I already teach you how to calculate the stress around the tunnel. When the pressure keeping increase, then the rock, the surrounding rock, will be broken because of the tensile stress. When you apply a pressure here, then the inner pressure will increase. If the pressure keeping increase, and finally the rock will fail because of the tensile stress, tension stress. Then the crack will propagate. So we can try to measure the response from the pressure rise up and the pressure dropping down because of the occurrence of failure. So the failure of the rocks will highly related to the in situ stress. So we can determine the in situ stress using the hydraulic response. Here I want to introduce you another two methods briefly. The first one will be the slip fracture. We will not try to use the water to make the rock broken down. You will try to use a mechanical device where it can expand freely. So if you have a device can expand like this, you can also apply a high pressure around the tunnel wall, around the borehole wall. Then the borehole can be damaged as well. This will be the slip fracture. And the third one will be the hydraulic test of pre-existing fracture. For a typical hydraulic fracture, we will try to find an intact part of the borehole. You will try to find the competent, a very good rocks without fractures. So when you apply a pressure, then all of the solution can try to use the elastic solution, like the Kirch solution. So you will try to find an intact part for measure the in situ stress. But for a hydraulic test on pre-existing fracture, it will be easy to understand. When you try to apply a pressure into a segment with a fracture there, when you increase the top pressure, then the fracture will open. when the pressure exists or the pressure over the normal stress acting on the fractures. Correct? So when the pressure larger than the normal stress of the fracture, then the fracture will open. If you can find 6 fractures with different orientation, then you can determine the normal stress acting on the fractures with different orientation. Why 6 fractures? Because you have, for the in situ stress, you will have 6 independent components. For a stress tensor, you will have 9 components, right? In general, you will have only 6 independent components for the in situ stress because of the symmetry. The stress tensor will be symmetrical. So you will have only 6 independent components. Can you understand? It looks like feel like sleepy still, right? Me too. So because you have totally 6 independent variables, so you need to have a 6 equation to solve the unknown. So that is the reason why you need to have the fractures with different orientation and measure the normal stress acting on the fractures. This will not so common because of you need to find a very good fractures, single fractures with different orientation. But this kind of technology is already well developed, and how to solve it is well developed. So this one will be the most common testing method to derive the in situ stress. So please do not confuse with the hydrofracturing technology, where you want to obtain more or enhance the recovery or enhance the production of oil or oil gas. Maybe you already hear this technology, we call it hydraulic fracturing, trying to enhance the production of oil, especially for the shale oil or oil shale. Traditionally, we were trying to find a reservoir like sandstone, where the permeability is pretty high. For oil industry, we were trying to produce the oil or gas from the porous sandstone because of the storage is large. But there still have some oil or gas stored in the shale, within the shale, where the shale have a very low permeability. Because of the low permeability, even though there are still some oil or gas inside of shale, but the low permeability, so the efficiency to get the oil will be pretty low. So we were not trying to get the oil from the shale. But some technology is starting to establish. We call it a hydraulic fracturing. We were trying to apply a pressure inside the borehole and trying to frac, make the shale frac. When the shale was fracked, then the permeability will increase. Then you can get the oil and the gas from the shale, from the shale. 通常这个叫做水力破裂法，以前都是从砂岩里头去生产石油或天然气，因为它非常的透水。那你要从页岩里头去生产这个油或者天然气，没有效率，因为它的渗透率太低了，所以后来就发展了这个水力破裂法。这个水力破裂法尝试去在孔里头把这个页岩把它劈裂， 那把页岩劈裂以后，它的渗透率就会增加，那我们就可以很顺利的取到就是这个天然气供应。所以美国因为就是这个技术发展起来了以后，它的这个石油跟天然气的这个量就大幅度的增加，所以导致有一段时间石油跟天然气的价格开始下跌，原因就是因为这个技术的这个发展。But we still have some issues related to this kind of technology. Some geoscientists or seismologists, they already identify the earthquake from the low seismicity area because of the production of oil and gas. It is not the so-called traditional field for oil or gas. Because you inject a lot of fluid pressure into the crust, so it triggers earthquake. So this makes somebody worry about this kind of problem of this kind of issues. Okay, so today I will mainly focus on the hydraulic fracture to measure the in situ stress, but this is totally different from the hydrofracturing technology to produce the oil or gas. It's a different thing, okay? Please do not confuse these two. Okay, there is a limitation for the hydraulic fracture method. If it wants to measure the in situ stress in shallow depths, then it could not success. Usually, it will not be success. Why? When you try to understand those methods, please also try to understand the limitation or advantage or disadvantage for those methods. No method is perfect method. Each method has its limitations. So you need to understand how to use different methods in the right condition. Okay? For the hydraulic fracture method, the problem will be the depth. Maybe you still remember I showed you a plot of the cave versus depth. So near surface, the cave could be relatively high. The K will be the ratio between vertical stress and horizontal stress, right? So if K larger than 1, it means the horizontal stress larger than the vertical stress, especially in the lower part. You still remember, okay? If the vertical stress is the minimum principal stress, then when you apply a pressure within the borehole, you cannot have the fracture like this. Can you understand this fracture will be the vertical fracture? When you see like this, and then you expand this, and you will have the fracture in this direction, vertical fractures. If you have a minimum principal stress in the vertical direction, then your fracture will be the horizontal fracture. Can you understand? The rock will failure follow the lowest resistance. If the vertical stress is the minimum principal stress, then you will have the horizontal fractures, because it is the most it will be the easiest generate fractures. Can you understand? 如果要是最小阻力就是在垂直方向，你加压它一定产生水平裂隙，因为那是最容易形成的裂隙。它要开一定是往最容易开的方向开啊，对不对？If the fracture is horizontally, then you can measure the vertical stress only. Then why do you need to measure the vertical stress? You don't really need the vertical stress, right? You want to measure the horizontal stress. Because of the vertical stress can be reasonably estimated. It will be the unit weight times the depth. 垂直应力很好估计啊，就是深度乘上单位重啊。所以你干嘛要量垂直应力 ？Okay, so that will be the limitation of the hydraulic fracture rate. We still have some method related to the so-called stress relief, as I mentioned to you previously. We were trying to release the stress around the rocks. So there is a technology we try to attach some strain gauge on the rock surface and trying to overcall it, so-called overcall. You have a strain gauge here. And I trying to drill in a borehole. We drill in a borehole to isolate this part to the surrounding rocks. Then the rocks will be unloaded. Then the rock will deform. Okay? If you unloaded a rocks, then the rock will deform. The unloaded stress will related to the deformation because you know the stress-strain relation. So you measure the strain, then you can estimate. You can estimate the in situ stress. The idea will be something like this. So can we try to use the we call it the door stopper or overcalling technology? Via the borehole. It will be difficult. If you want to measure the stress at the depth like 200 meters or 300 meters, then it will be extremely difficult to conduct the test like this. You need to drilling a borehole and polishing the surface and the stitch and to try to attach the strain gauge on the surface and drilling a borehole through the strain gauge. It will be extremely difficult if you want to get it from the ground surface to measure the in situ stress at the depth like 200, 300, 500 meters. So for this kind of technology, you need to have a free surface to measure, like a tunnel wall or like a shape wall, like I mentioned to you. You need to get there. To get where you want to measure the in situ stress, you need to have some equipment there. So you cannot use in borehole. Understand? So that is, I always remind you how to get there to conduct your measurement. It will be a very important point. Okay? And I already mentioned to you the second approach. We call it a compensate approach. We try to release the stress and trying to apply the stress again. When you relieve the stress, then the rock will deform. So you're trying to apply a stress, make the rock go back to the original position. Then you can try to evaluate the in situ stress. So we call it the stress compensation method. So you have the fracture method, stress compensation method. The most commonly used technology will be the flapjack method. We were trying to cut a slot in the tunnel wall, like this. This will be a slot. If you cut the cross section, it will be like this. You cut the slot. Like this, you cut the slot into the tunnel wall. Before you cut the slot, you will make a mark like this. And you will try to measure the distance between those marks. Then you will keeping monitoring the distance change for those marks. Then you will cut a slot around here. When you cut the slot here, you can imagine those marks will close to each other, right? Over here. When you cut the slot, those marks will approaching. Okay? And you will insert a flat jack. Do you know jack? When you are a tire of your car broken, you need to have a jack to lift the car and to change the tire. Okay? So you will put the flat jack here and try to increase the pressure. And the jack will try to make the slot open again. So you will try to measure the displacement. Like this, when you cut the slot, they will close to each other. So the displacement will have a negative value like this and approach a steady state deformation. And when it goes to the steady state, then you will starting to make your hydraulic, make your jack expand. So the displacement will go back. When it goes back to the original distance, then you record the pressure of the jack. So this will be the compensated stress to make the rock slot go back to the rocks surrounding the slot go back to the original position. Okay? Again, can you doing this inside a borehole? It is impossible unless you can shrinkage yourself. So you need to have a space to conduct the experiments like this. You need to have equipment. So you need to have a tunnel. So as I mentioned to you, for the tunnel engineering, we usually have some shape or some edits for the side investigation. 常常隧道工程会有一些探查坑，所以我们会利用这些探查坑进行现地应用。Or sometimes you will have some advanced tunnel, like 雪山 tunnel. We have a advanced tunnel. Before the main tunnel driven through, we drill a small tunnel. This small tunnel can be the site investigation. You can go in a small tunnel. It will be more easy to drill in it. So you can try to make the geological mapping during the drilling. And you will have the benefit if you have a small tunnel beneath the main tunnel. Then this small tunnel could be the drainage path for the groundwater table. So you will have less groundwater related problems. So the other benefit, this small tunnel can be used for the maintenance for the main tunnel after the tunnel complete. So there are several usage for the advanced tunnel. So if you have the advanced tunnel, then you can try to use this tunnel to measure the institutions. Okay, understand? You need to have a space to do this. the basic idea for the compensated stress method, you will have the stress at the different locations. At the tunnel wall and at the tunnel roof, you will have a different measurement like this. Then you can try to calculate the in-situ stress. Okay, I will mention this to you later. But for this kind of technology, you will have some problem or some limitation for this kind of method. What kind of problem? When you drill in a tunnel, like I mentioned to you, you will have some disturbance area around the tunnel. So the tunnel will have some micro crack effect around the tunnel wall because of the high stresses. You will have a high deviatory stress. Do you still remember? It will be equals to 3 sigma V subtract the sigma H, or 3 sigma H subtract the sigma V. Okay, so you will have a high deviatory stress. Then you will have a disturbance zone around the tunnel. And this disturbance zone will make your measurement complicated because of the plastic deformation. Okay? So this kind of problem will not easy to overcome for this kind of method. There are two important inference for the tunnel wall excavation. One will be the excavation technology. You could try to use the drilling and blasting and D&B method to excavate the tunnel. Drilling the borehole and put the dynamite and expose it and trying to remove the rocks. This process could damage the rock surface. The other will be the stress concentration. Because you have a stress concentration and make the high deviatory stress, and you will influence the rocks surrounding the tunnel wall. So this will be the influence of the disturbance. Okay, so we could try to use some method like I mentioned to you. I will try to drilling if we have a tunnel or ship edits for the geological survey. And here is the tunnel wall, and here is the place you want to measure the in-situ stress. And you will try to attach a strain gauge like this, and trying to drilling a borehole surrounding the strain gauge. And maybe you can try to mark several pins like this. If you have a tunnel, and here is your tunnel wall, and you're trying to put how many pins here? 7 or 8. You have 8 pins on the tunnel wall. After this, you are drilling a borehole and take the rocks out. Then the rocks will deform. Because if you drill in a core like this, then you unload it. Then this will deform. Okay? Another approach, I will not try to measure the deformation for the rock inside the borehole. We will try to put the pins surrounding the borehole. The pins like this. And drilling the borehole and take the rocks out. Then what happened? Those marks will move toward to the borehole. Okay? So these two kinds of technology. One technology we call it overcore. if you put the strain gauge inside the rock and drilling a borehole outside the strain gauge, we call it overcoring. 中文叫做套砖法，套过去嘛，套砖法。If you measure the deformation surrounding the borehole and you drill in the borehole and take this rock out, and those pins move toward this borehole, we call it undercore. Can you understand? 这种叫做内砖法，所以我们有套砖法跟内砖法，这样子钻进去叫内砖法。你strain gauge贴在这里，然后外面钻下去，然后释放这个压力，让中间的那个岩石变形，这个叫做套砖法。可不可以想象什么叫做套砖？什么套砖？什么叫做内砖 ？OK， so overcore, undercore, two technology. If you have the measurement at a different location of the tunnels, here you're trying to measure the in situ stress, and here you're trying to measure the in situ stress. Then you can try to infer the in situ stress. Why you need to have this kind of transformation? Please think about if your K not equal to 1, it means if your vertical stress and horizontal stress is different, then the sigma theta here and the sigma theta here will be different. 记不记得 ？One quick example. Here could be 3 sigma v subtract sigma h, and here will be 3 sigma h subtract sigma v. So the sigma theta here and the sigma theta here will be different. If you measure the stress here and measure the stress here, then you will have two equations to help you to solve the really in situ stress. Okay? So you are not really trying to understand the sigma theta. You're trying to know the sigma xx and sigma yy. You need to back calculate it. Okay, for this kind of technology, we call it the relief method. So right now you have 3 different kinds of in situ stress measurement, right? The first one will be the fracturing method. You make the rock damage or make the rock fracture, and you will measure the hydraulic response. Then you can obtain the in situ stress because they have some relation. And the third one, the second one will be the stress compensated method. The most commonly used will be the flapjack method. So you're trying to relieve the stress and trying to apply the stress again and make the deformation go back to the original positions. That will be the stress compensation method. For those kind of methods, no matter it is the undercore or overcore technology, they will be categorized into the so-called relief method. You try to relieve the stress and try to measure the displacement or deformation, and you try to back calculate the in situ stress. For these two kinds of approach, we call it the surface relief. If you have a tunnel and you make the pins and drilling a borehole, and you can measure the displacement, right? But where you relieve the stress, you relieve the stress around the tunnel or shaft. Or you can put the strain gauge here on the surface of rock or of tunnels, at tunnel wall or at the roof of the tunnel. And you're trying to overcall it, and the stress will relieve Where the stress relief? The stress relief around the tunnel wall, tunnel surface. So we call it the surface relief. Okay? For this kind of surface relief method, you will have the same problem or issues related to the disturbance around the tunnel. Do you still remember? If you drill in a tunnel, then you will have some disturbance around the tunnel. To reduce the influence of the damage zone, you want to doing your measurement in good rocks, but not the damaged rocks. So you can try to drilling a small borehole. For example, if this is a tunnel wall, I drill in a borehole like 50 centimeter, half meter, okay, and try to use some machine to polish this surface. And we try to make the strain gauge attach on the polishing surface tightly. You don't really have the chance to doing the uniaxial compression test for rocks. Usually you need to attach the strain gauge on the rock surface tightly because you want your rock deformation is identical to the strain gauge. So you need to perfectly attach the strain gauge on the rock surface. It will be the same idea. You will try to attach the strain gauge tightly on the polished surface of the rocks. Then you can overcome the surface disturbance a little bit. So after you put the strain gauge like this, then you will drilling a borehole here. Can you understand this figure? This will be the borehole like this one. And you will put your strain gauge here. And you will drill in a borehole here. So using this kind of method, you can reduce the disturbance of the tunnel wall a little bit, not totally. But it will be difficult for this kind of measurement. It will be difficult to doing things like that. Okay? So you still have the problem related to the stress concentration. Because of your measurement here, you really measured the field. I remember you have homework here. Maybe you already did this homework. The distribution of the sigma theta and the sigma r, right? So the sigma r and the sigma theta always change with distance to the tunnel surface. Okay? For this kind of measurement, you always try to measure the sigma r or sigma theta. Could it be possible to overcome this, to obtain the in situ stress directly, not really trying to convert the major stress to the in situ stress? Please remember, always remember, what did you measure? Are you measure the sigma xx, sigma yy, or you are measure the sigma r and the sigma theta? I hope I did not confuse you. If the measurement for sigma r and sigma theta is different from the measurement for sigma xx and sigma yy. In the local coordinate system or in the global coordinate system, it will be okay if you try to measure the sigma r and sigma theta. It will be okay. because of the sigma r and the sigma theta is related to the sigma xx and the sigma yy. So you can convert it. But you always need to remember, what did you measure? You measure the sigma r, sigma theta, or the sigma xx and sigma yy. Do you really need to convert it back to the in situ stress? Sometimes you need to doing this kind of conversion. Okay? So we have the borehole relief to overcome the issue related to the stress concentration. Do you still remember what is the idea for the stress relief? We try to measure the deformation of rocks after we relieve the stress. So the previous introduction for the stress relief were related to the stress relief surrounding a tunnel. Do you still remember I told you? With the exception of the hydraulic fracture, other methods you need to have a borehole or shape or ethics to conduct the test, right? If you need to have a borehole, if you need to have a tunnel, ethics, or shaft to doing the measurement, then you will have the problem related to the tunnel disturbance, excavation disturbance, or the stress concentration problem, high deviatory stress. You will have this kind of issues exist. But the so-called borehole relief can overcome this. What is the borehole relief? Previous displacement or deformation measurement, we are trying to use a strain gauge attached here. Okay, we will put the strain gauge here, like this, or we will try to make some pins on the tunnel wall and overcoat it or undercoat it. Then the stress will relieve, the rock will deform, and I can measure it. The borehole relief, we're trying to put the sensors like strain gauge or the displacement markers in a small device like this. Maybe it's not really easy to see, or maybe it's not invisible for this part. This part will be the strain gauge. Okay? And you will have a strain gauge around this small device. So we were trying to drill a borehole outside the inference zone. And I was trying to put the gauge inside the borehole and left the device there. And I was trying to overcoat it. Then I can measure the displacement related to the stress relief. Then I can back calculate the in situ stress. In this case, this location already away from the disturbance zone, like 2.5 times the diameter or 5 times of the radius of tunnel. Do you still remember this part? When the distance away from the tunnel wall, the stress, sigma theta and sigma r, will go back to the sigma xx and sigma yy. It's around 5 times of the radius, or 2.5 times of the diameters. Okay? So I drill a borehole like this to here, and drill a small borehole, and put this device, put these sensors into here. And I need to have some wires, of course, because you want to measure the deformation, so you need to have the wires. You have wires to the tunnel wall. After you fix it here, and it is confirmably tightly attached to the surrounding rocks, then I will try to drill in a borehole like this. Then the stress here will be released. Then the sensor will start to measure the deformation of the rocks. So we can try to solve or calculate the in situ stress. Understand? If for the final examination, I give you a question like, please list the in situ stress measurement method. Please list the methods and trying to make some comments on the advantage and the disadvantage of this method. Can you answer me? So I try to use 50 minutes to introduce you the different methods and what is the advantage and the disadvantage of different methods, right? So please think about what I told you. If I ask you a question like this, how can you answer it? Okay? So there are a lot of the device looks like this. So different company design different device to help you to measure the institutions. Okay? So I will go back to the original question. So we have this kind of device. Can we measure the in situ stress at the correct depth? For example, 1 kilometer. It will be extremely difficult. So you can try to use this technology to measure the in situ stress. Of course, you have a borehole, but this kind of borehole is totally different from the hydraulic fracturing conduct at the ground surface to drill in the borehole like 1 kilometer. It will be easy to operate for the hydraulic fracturing. You only need to inject the water into a borehole. But for this kind of measurement, a lot of precise work need to carefully conduct. So you have a borehole like 10 meters, I think it will be okay. But 100 meters, it will be difficult. 1 kilometer, it will be almost impossible. Okay, so you need to understand the different methods and the limitation of different methods. Then when you graduate, when you try to doing something, you will doing it correctly. Okay, you will not make a big mistake related to those. Okay, I will stop here, and next class I will try to teach you how to solve the in situ stress via hydraulic fracture method. I did not go into the detail about the analysis, right? I just overview. I give you an overview of the different methods. But next class, I will give you some detailed introduction for the measurement. Okay, so I was talking about the hydraulic fracture method. So you need to always remember though this part where you already write the homework about this. And please remember, right now we're trying to look downward. So it will be the top view. It will be not the sigma V and sigma H. All of the surrounding stress will be the sigma H maxima and the sigma H minima. Okay, we have sigma V, sigma H in two different directions. So we're trying to solve the sigma H maxima and the sigma H minima, and the direction of the sigma H maxima and the sigma H minima. The procedure was something like this. We were trying to drill in a borehole and put the paper from the surface and lowering down. Put the first paper here and put the second paper here and flat it, not flat it, to inject the pressure to expand it, to seal this segment. This segment will isolate to the upper part and lower part. After this, I was trying to inject the pressure into the borehole, and we were trying to measure the pressure rise up and decrease and lowering down. So we were trying to increase the flow pressure from the hydrostatic pressure, because you have some water within the borehole, so you already have a pressure in the segment. Okay, you have water inside the borehole, so the groundwater table, so you will have water. And we're starting to increase the pressure in the segment, in this segment. And the pressure will going up, keeping going up, and to certain value, the pressure will starting to dropping down. What happened? The rock cracked. You have a fracture occurred. When you have a fracture, the water will flowing out, so the pressure will dropping down. Okay? So you will have the so-called PC1. You will have one value here. The pressure will keeping dropping down, and then we'll have a steady state. The pressure will remain there, unchanged. Till the curve going to the steady state, you will close the pressure. You will close the pump. Then the pressure will dropping down rapidly. And relatively a little bit lower than the hydrostatic pressure, because of you have new fractures. Relatively, it will be similar. And you open the pump again to inject the pressure into that segment. The pressure will develop again. Okay? Develop again to a peak value. The pressure will starting to decrease. You must notice something. What did you notice? The peak value, the second peak value, we call it PC2. The PC2 is lower than the PC1. Okay? And when you going up to PC2, naturally, the pressure will starting to decrease to a steady state again. And this steady state was similar to the first cycle. I was trying to explain to you the mechanism related to the name. The first one, the rock will crack, so you will have a new formed fractures. So the water will flowing out, right? For the second time, you don't really need to make the rock fracture, because the rock already fractured. Okay? So the only things you need to make the water flowing out, you need to overcome the stress applied on your rock. So that is the difference between these two. What is the difference between the PC1 and PC2? It will be highly related to the tensile strength of rocks. Can you understand? For the first time, you want to make the rock fracture. You need to overcome the in situ stress, the first one. And you still need to overcome the tensile strength of rocks. But for the second time, you only need to overcome the in situ stress. Because the rock already fractured, so you don't really have the tensile strength. The tensile strength of the rock already reduced to 0. That will be the difference between these two. What stress you need to overcome to make the fracture open? What do you think about that? What stress you need to overcome it? Here, you need to make this fracture open. What stress you need to overcome? Sigma theta, right? Do you understand? You want to make this fracture open. Here you have a tangential stress acting on here. The radius stress equals to 0 because it is a surface, free surface. So the sigma r will equal to 0. If the in situ stress is hydrostatic, I hope you still remember the sigma r will equal to 0 and the sigma theta will equal to 2p0. Alright? Under the hydrostatic condition, so the pressure need to overcome the 2p0, then you can make the crack open. Okay? So this pressure well related to the sigma theta. Okay. Then what is this? When the fracture starting to open, then the fracture will propagate. Correct? The fracture will propagate. Can you understand? The sigma theta will reduce with the increasing distance to the center of the ball. That's the reason why I asked you to write this over. Sigma r and sigma theta, right? Sigma r will increase with the distance to the tunnel center. But the sigma theta will reduce with the distance to the tunnel center. So, when the pressure overcomes the sigma theta around the tunnel wall, the resistance will decrease with increasing distance. The sigma theta here is maximum. After this location, the sigma theta will become smaller and smaller. And finally, the sigma theta will go into a steady state. Correct? So here, you will overcome the sigma theta at the tunnel wall. After this, the required pressure to make the fracture open will become less and less. So it will be decreased and go into a steady state. So the steady state pressure around here, I don't remember, PC or something. This pressure will highly related to the sigma theta at the infinite distance to the center of the tunnel. You need to understand a basic idea for the hydraulic fracture. I will give you equation right now. Okay? So as I mentioned to you, you have the so-called shut-in pressure. It will be the steady state shut-in pressure. And you will have the PC1. This will relate to the crack forming, fracture forming. And PC2, it will be related to the crack opening. The difference between these two will be the tensile strength of rocks. So, equations. Kirch solutions. Again, we only need the sigma theta. At least the sigma theta there. So at the point A here, it means the theta equals to 0 or 180. You can calculate the sigma theta like this equation. Right? You're already familiar with this. When the pressure equals to PC1, the pressure is equal to the sigma theta plus the tensile strength of rocks. Correct? So the pressure minus the tangential stress will equal to the tensile stress. Okay? Or the PC1 equals to the sigma theta plus the tensile stress. It will be the same. The same idea. Understand? I can ask you to derive this because it is not difficult. And I already obtained the sigma theta from Kirch solution. So I can put this to there. So the sigma H maxima will equals to this equation. And the second, the crack will propagate when the pressure equals to the Ps. The crack will continue propagate if you have the pressure equal to Ps. Okay? Then you will go into a steady state. So the Charlene pressure will equal to the sigma H minimum. Please consider here, if you have a fracture in this direction and keeping propagating, what is the sigma theta change? Sigma theta will change from the maximum value equal to this and gradually decrease to a steady value equal to sigma H minimum. Why? It will be equal to the boundary stress. No stress concentration. So if you have a crack continue propagate to a long distance, the normal stress acting on this fracture will equal to the sigma H minimum. Okay? So this will equal to the sigma H minimum. And the next one. If you know the T0, then this equation can be solved because you have only two unknowns. You have one unknowns, two unknowns, three unknowns, and you have two equations, right? But if you know the T0, then you have two equations and two unknowns. What is T0? As I mentioned to you, T0 equals to PC1 minus PC2. So anything has been solved. But as I told you, when you determine the in situ stress, you will not only satisfy with the value of the principal stress, you also want to know the direction of the principal stress. How can you obtain the direction of principal stress? We were trying to use the 4-hole camera again, or trying to use some technology to lowering it down and to pressure it and to have some stamps to record the fracture orientation. Or trying to use the borehole camera, lowering down and scan the borehole, and lowering down to the segment where you make the experiments, and you can find the orientation of the fractures. For example, if you find the fracture occurred on here and on here, if we know here is the east and here is the west, then where is the maximum principal stress? Can you tell me the principal directions of principal stress direction of the maxima horizontal stress? It would be in east-west direction. It would be the maximum principal stress direction. Because the fracture will propagate along the least resistance. Where is the least resistance? You have sigma theta equals to 3 sigma h minima minus sigma h maxima, right? How about along this direction? This direction will be 3 sigma h maxima subtract sigma h minima. This barrier will be larger than this one. So the fracture suddenly will propagate along this direction. Okay, can I give you another example? If this is the borehole camera record, and this will be the north, this will be the east, and the west, no, south, and the west, and the north again. You will unfold it. It will be a circle, right? And you unfold it. And you clearly observe the fracture is around here. What is the direction of the maximum principal stress? If we call it the east, it will be northwest. The orientation of the fracture will be the north 50 degrees to the west, right? If I draw a borehole like this, where is the fracture occur? The fracture will like this. Then where is the maximum horizontal principal stress? The direction. You can understand this direction should be the sigma h maxima, and this will be the sigma h minima, because in this direction will be the next resistance. Alright? Is it simple? Please remember one thing different from this result. Do you still remember borehole breakout? If you have a borehole breakout like this, where is the maximum principal horizontal stress directions? This will be the borehole breakout. The borehole breakout will occur because of the high deviatory stress. How about this condition? No, it will be inverse. For this case, you will have the sigma h minimum around here, and you will have the sigma h maximum in this direction. Why? It will be different, right? Because this kind of crack or this kind of damage is related to the compression stress. We don't really try to increase the pore pressure in this segment. The fracture is due to the principal stress itself. The fracture of this is because of the pressure, because of the large pressure inside the borehole. Okay, for this kind problem, like you have a balloon and you try to increase the pressure, and finally the balloon will blow up. So you increase the inner pressure. How about this? This is like a can, and you try to squeeze the can, and the can will damage. So you can imagine, if you have this, you should have a very high sigma theta around here. If you have a sigma theta maxima, do you still remember? If you have a damage here, it means you have a sigma theta maxima, and make this rock broken down because of a very large deviatory stress to make it broken down. Here you don't really notice anything because here you will have the sigma theta minimum. Do you still hear me? Or you are totally confused? I think I make a very clear statement about this. If you really concentrate yourself and listen to me. So if you have a damage here, it means you have a maximum deviatory stress can crush the rock. Okay, so for the borehole breakout without any injection of pressure inside the borehole, the rock will damage like this, and you will have the maximum tangential stress here. It means you will have the maximum principal stress or horizontal stress in this direction. Okay, or maybe I will tell you another way. For the same borehole, before you inject the pressure, the rock could have some damage around here. This will be the borehole breakout. How it forms? How it forms? Sorry, I need to change the shape a little bit. The fracture will not really open like the one I drew to you. The hydraulic fracture will have the fracture like this. And for the borehole breakout, you will have this damage of rocks. Okay. Before you doing this, I give you the direction of principal stress. The sigma H minima will be here, and the sigma H maxima will be here. Then what? How about the sigma theta? The sigma theta in this direction will be. Can you tell me? Three sigma H minima minus sigma H maxima, correct? How about here? Three H maxima minus sigma h minima. If I give you a value, okay, for example, sigma h maxima equals to 10 MPa, sigma h minima equals to 8 MPa. Can you tell me the sigma h? Sorry, the sigma theta in this case. So this will be correct. How about this? $22. Correct? So where you will have the borehole breakout? Certainly you will have a borehole breakout here. Because the sigma theta here is larger than here. So the rock will crush because of the high deviatory stress. Okay, so this will be the one thing. Then I give a pressure inside the borehole and increase the pressure. And you have some vertical fracture flow and propagate. Where should it appear? It should appear here. Because you have the smallest sigma theta here, so you will have the least resistance for opening of the fracture. It will be easier to make the rock fracture here, but not here. So can you distinguish the difference between the orientation from the borehole breakout and the orientation from the hydraulic fracturing? One is to increase the pressure inside the borehole for the hydraulic fracturing. And for the borehole breakout, it will be induced by the high deviatory stress, make the rock crush. Okay? So all of those, you need to have the idea about this homework. If you write this homework by yourself, you can easily understand what I'm talking about. If you did not write the homework by yourself, it would be extremely difficult for you to understand things like that. Okay? Any question related to this? If I lowering down the borehole camera and I found the fracture like this, but not vertical. This will be vertical, right? So it will be appear two times around a hole, here and here. So when you take the video, then you will observe it here and observe it here. If you take a camera shot around the borehole and then you find a fracture like this, please remember you will still have this. You will have this curve as well. But if you have a fracture like this, you will not try to analyze this. And you will directly say, oh, the experiment is failed. Why? If you have a fracture like this, or like low angle, like this, low angle fractures, nearly horizontal, like this. You don't really have any information related to the horizontal stress. You only have the information in this direction. The fracture overcome the vertical stress, but not overcome the horizontal stress. the deviatory stress in the horizontal plane. So you've got nothing. If you don't really understand this, then you could continue to analyze the results. It will be meaningless. Okay? So, when you will have a horizontal fracture and when you will have the vertical fractures, please tell me. We can go back to this plot. When? Please think about it. Can you see? Even this?
I can see the other line, so I can.
It's okay. When you will have a vertical fracture and when you will have a horizontal fracture. Please follow me. If the vertical stress larger than 14 MPa, then you will have a vertical fracture. If the vertical stress smaller than 14 MPa, then you will have a horizontal fracture. It's so easy. Because the fracture will form for the lowest resistance. The lowest resistance in the horizontal cross-section will be 14 MPa. We can draw a plot for the sigma theta around the borehole. The maximum value will be 22. The smallest value will equal to 14. And other orientation will in between. Correct? So since the smallest tangential stress equals to 14 MPa, if the vertical stress smaller than this value, then you will have a horizontal fractures. Because it is least resistance, the most easy to form. Okay? So using this, you can try to evaluate the successful condition for your hydraulic fracture test or for your measurement. This will be the condition. Okay? So if you trying to plan or you trying to organize an experiment where you want to measure the in situ stress via hydraulic fracture, you need to assess beforehand. Although you don't really have the stress value, but you can try to find the literature or find the measurement around your region and try to understand the sigma h minimum and the ratio between sigma h minimum and the sigma h maximum. Okay, you can try to find some standard value from the literature, and you can try to evaluate the successful segment for this meeting. Okay. Then the fracture method. As I told you, we were trying to excavate a slot and trying to measure the distance between two pins. And you will have this kind of results because the pins will close to each other, will approach to each other. And you put the hydraulic jet into the slot and trying to increase the pressure, the distance will starting to go back. When it goes back to the original position, go back to the original position, then you will have a PC. What is this? Please go back to the curved solution, okay? But this time, you have a vertical direction and horizontal direction. The horizontal direction will perpendicular to the tunnel axis. You have a tunnel like this, right? So you will have a vertical stress and a horizontal stress in this direction. If you have a tunnel. Again, the curved solution. To avoid confusion, to avoid make you confused, right now I use pH and PV. Okay, not sigma. I'm trying to use P, but this well related to the stress, but not load. Okay, so you will have the horizontal stress equals to pH, and you will have the vertical stress equals to PV. When you make the measurement, sorry. So what happened? Okay. So you will try to measure the stress at the tunnel wall and on the roof of the tunnel. Then what stress you measure? If we call it the compensated stress, PC. Actually, this PC will equals to the sigma theta. Again, you push it, go back to the original location. You're trying to compensate the sigma theta. Correct? But you will have a different sigma theta here and here. The sigma theta will be different. How about the sigma theta at the tunnel wall? The sigma theta at the tunnel wall you will equal to 3 times the PV minus pH. Right? And the stress at the tunnel roof will equal to 3 pH minus sigma V. You have two unknowns, pH and PV. You have two equations. So you can solve pH and PV if you can measure the sigma theta W and the sigma theta R. Okay? I think I don't really need to give you some numbers again. Okay. So usually you will try to have the measurement at the tunnel wall and have a measurement on the roof of the tunnel. Then you can evaluate the sigma, the pH, and the PV. Okay, then the surface relief. When you talk about the hydraulic fracture and talking about the stress compensation, we don't really need the relation between stress and strain. Right? We don't really measure the strain. We're trying to compensate the stress, or we're trying to apply a stress to make the rocks failure. So it has nothing to do with the stress-strain relation. But for the relief method, stress relief method, we try to relieve the stress and measure the strain or displacement and try to infer or calculate the stress. So certainly, absolutely, you need to have the stress-strain relation. Okay, it will be the most different things. I was starting from the undercoring. This will be the undercoring. So I have a tunnel wall here, and I put 8 pins around the tunnel wall and undercore it. And take the rod core out. So you will have a hole. And all of the pins will move toward to the center of the hole. Do you still remember the current solution? I give you another pair of equations in the right-hand side, lower part of the right-hand side. It will be the UR and UC. We never talked about this before, but right now you need it. You can imagine the displacement between this point and this point will be the 2UR. The radial displacement. 2 times, because you have a UR, you have UR, if it is symmetrical. So the displacement between this and this will be the 2UR. Can you go back to have a look at your PowerPoint? I don't really want to go back. Maybe I have some slides below. No, I don't really have it. This will be the layout of the overcoring. Usually we call this a door stopper. In Chinese we call it 门子法. I don't know what this means. I don't know what is door stopper. But we will polish in the surface and we will try to attach the strain gauge firmly. If you want to overcome some disturbance around the tunnel wall, you can drill a large borehole like this and polish in this surface and attach the strain gauge. The strain rosette, you already learned it. You have 3 different directions, so you can calculate the epsilon x, epsilon y, and gamma xy. And we were trying to drill a borehole over the strain gauge. Then the stress around here, outside here, will be released. So we call it overcore. Like this, overcore it. Then the strain will be the stress will be released. So if you overcore it, and you will have epsilon A, epsilon B, and epsilon C in 3 different directions. Then you can calculate the epsilon x prime, epsilon z prime, and the gamma x prime z prime in this coordinate system. Coordinate system will be very important. You need to clearly describe the coordinate system. Sometimes you need to transform the coordinate system. I think I spent a lot of time in the very beginning for this class to teach you how to make the coordinate system transformation for stress and for strain. You already learned this from a homework, right? So you are pretty understand if you have the strain rosette like this, and you have epsilon A, epsilon B, and epsilon C. Then you can solve the strain in this direction and in this direction and the shear strain. Okay. Then you want to have the release stress. You can calculate the relation between the strain around here and the released stress. This will follow the elastic relation. You will have some unload. So usually when you loading, you could have an elastic strain and plastic strain. When you unload it, you will only have the elastic strain recovery. So we can try to use the elastic relation to derive the released stress. And the released stress here well related to the in situ stress around here. Understand? They will have some relation. So this relation is derived from the finite element analysis. It will be a little bit compressed. So you measure this, you will have this, and you can derive the stress difference from the elastic relation, and from the finite element analysis, you can derive the stress state at this point. Please remember, the stress here will be the stress after the stress concentration, because you have a tunnel. So if you excavated a tunnel, the stress will change around the tunnel. This distance is not far enough. So in this place, it's still influenced by the stress concentration. So you will try to have a different measurement to derive the global in situ stress. So you will assume near the surface, you will have x, z, and y in this direction. You will have x, z. This will be the top view. You will have x and z. And this direction will be the y. This direction will be the y. If your measurement is very close to the tunnel wall, so if this is a very short distance, very close to the tunnel wall, very near the tunnel wall, you can understand the radial stress will almost equals to 0. So you will assume the sigma y prime equals to 0. So you will have 3 unknowns to be determined. I will mention this later. You will measure the stress, sigma x, sigma z, and tau xz. But this is not the global stress. I will mention this later. This will be another surface relief method. This will be a undercore. So you put some pins and you drill a borehole and take the rock out, and the pins will move toward to the center of the borehole. So the displacement at any location can be determined by the Kirch solution. So I can express in this form. And the coefficient will be function of the elastic constant only. Of course, it will be related to the direction and related to the distance to the center of the borehole. Okay, so if you know the location of the pin, F1, F2, F3 can be determined if you know the elastic constant as well. Okay, so when you drill in a borehole and you will have the rock sample, you can try to use this rock doing the rock test to derive the elastic constant from the removed rocks. So the radial displacement will solely be function of stress. The stress will be the only unknown. So you measure the radial displacement and you trying to back calculate the stress. So you are undercoring it. So the displacement will related to the stress. You can observe all of the stress here by adding a prime. So all of the x prime, z prime will depends on the location of the tunnel wall. If you have a tunnel wall like this, so the x prime, z prime is different from the coordinate system in here. The x prime, z prime will be different for this direction and for this direction. So I add in prime, it will be the local coordinate system. Okay? So every single point when you conduct the surface stress relief, you can determine the sigma x prime, sigma z prime, and the tau x prime z prime at each single point. Okay, so it'll be quite easy. Right now, I want to mention more about the stress concentration multiplication. As I mentioned to you, for the door stopper and the overcoring technology, you can derive the sigma x prime, sigma z prime, and tau x prime z prime in a single point. It will be a local coordinate system, x prime z prime. Okay. And for another technology, we call it undercore. You can derive the local coordinate system stress tensor as well. You will have the local coordinate system. So here shows you a tunnel where you're trying to make the surface relief. You have a tunnel, you could measure the stress in this point and in this point. Like a flat jack. You still remember you have a PV and pH. So you will have a two variable or two unknowns. So right now you need to have a two equation. So I try to determine the sigma theta here and trying to determine the sigma theta there. So I will have two equations. So I can solve the PV and pH. The same thing for the surface relief. You can determine the sigma x prime, sigma z prime, tau x prime z prime. So you will have the point 1, for example here. The y always direct into the tunnel wall. So this will be x prime and this will be z prime in this point. Instead here, the y will toward to the tunnel wall. So this will be y, and this will be the z prime, and this will be the x prime. So you will have the sigma x prime, sigma z prime, and the tau x prime z prime here. And you will have another sigma x prime, sigma z prime, and the tau x prime z prime at this point. You will have two this. We were trying to use this to derive the global stress tensor. We are really care about the 6 independent component in the global coordinate system. So this will be the global coordinate system. The global coordinate system will try to use the tunnel axis as y. And you will have this as x and vertical as z. Okay. So you will have this vector, you will have this vector, and you will have this vector. And you have this coordinate system, and you can have this coordinate system. You already learned the directional sign, directional cosine. If you have a two coordinate system, then you can obtain the directional cosine. Do you still remember? This times this, this times this, this times this dot this, 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 this dot this. So you will have a directional cosine for 9 components. So any physical quantities, if the quantities are a tensor, then you can freely to transform this tensor from this coordinate system to this coordinate if you know the direction of the sun. You already learned this. It will be not a really difficult test. If you want to make your calculation, you can write a very simple program to make the calculation. You don't really need any software to help you. You can write the code by yourself. Okay? So, how to derive this from this and from this? No, I should not say that. How to derive this from the measurement, either for this or either for this. Okay? For this example, you will have a measurement for this three components at here and at here. And I will try to get this. Here shows you a general curse formula, which is proposed by Lehman at 40 years ago. This will be a three-dimensional relation. Any single point, the stress here will determine or will influenced by the global stress tensor. So right now you can imagine you have a tunnel, and you will have a three-dimensional boundary stress. Before you have only two-dimensional boundary stress, right? If I have a tunnel, and you have a boundary stress, sigma x, sigma y, for example, then you can calculate the stress at any single point. Right now, this will be a three-dimensional. If you have a tunnel, and I have a boundary stress, sigma x, sigma y, and sigma z, then at any single point around the tunnel, I can calculate the sigma x prime, sigma y prime, and the sigma z prime. Okay? Sorry. Sigma x prime, sigma z prime, and the tau x z. Tau x prime z prime. So they have this relation. This will be an analytical solution. All of this variable will be function of theta. What is the theta? Theta will be this. Okay? For example, at the tunnel wall, theta equals to 0, and in the roof, the theta will equals to 90. So at any single point, you will have this matrix, because this is solely related to theta. Okay? So using this as an example, theta will equals to 0, and you will have a relation. And theta equals to 90, you will have another relation. Okay? So how many equations you have? This will be the measured variable, right? You measure this. And this formula gives you three equations. Correct? So you measure this. This is a no matrix. You already know this. So this will equal to this time this, 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 and this time this. And this will equal to this time this, blah, 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 blah. So you will have a, this will equal to this time this, this time this, this time this. So here you will have three equations. Right? How many unknowns you have? This will be your unknown. 1, 2, 3, 4, 5, 6. So if you have two measurements, one here and one here, then you will have a 6th equation. Correct? I think I don't need to list it for you. Point 1, you will have 3 equations. This will be unknown. This will be the variable which already be measured. Okay? This will be solely depend on the theta equals to 0 or 90. If theta equals to 0, then you will have 3 equations. Theta equals to 90, you will have another 3 equations. Then you can solve this 6th variable. Okay? Usually, for the stress measurement, we want to have some redundant. What is redundant? We will try to 9 equations to solve the 6th variable to eliminate the possible auxiliary. So usually you will measure at 3 different locations. For example, you will have one measurement here, one measurement here, and one measurement here. Then you can have 9 equations and trying to solve 6 unknowns. And you will try to obtain the optimized solution. Can fit the 3 measurements. We call it a redundant. It means we need to check the correctness of the solve stress components. Like this. Okay, am I clear? Okay. So this will be the surface relief. If you have the borehole relief, then you don't need to make the straight concentration modification. So I will introduce you the borehole relief. Oh, before, yes, it will be the borehole relief. Usually the borehole relief will away from the tunnel wall to avoid any correction for the stress concentration. So this will be our only illustration. I will introduce you a USPM gauge, which is developed by the U.S. Bureau of Mining in U.S. Okay, so you will have a gauge like this, and you will have a 6 pin inside the gauge. So you can measure the displacement between these 2 points, and these 2 points. Understand? So I draw a line here. You will have a measurement in the blue direction, blue dashed line direction, green dashed line direction, and the brown dashed line directions. Okay? And I drill a small hole and put the gauge, USBN gauge here. And I overcore it. What happened? When you overcore it, the stress will be relieved. When the stress was relieved, the rock around here and here will deform. If the rock here and here deform, then the gauges here will deform as well. So you will measure the displacement along this direction, and this direction. So I will try to show you the measurement will be something like this. When you relieve the stress, and you will have a displacement along 3 directions. Like this. Again, you overcore it like this, and your 3 points will be formed like this. So you will measure the displacement along the brown direction, blue direction, and the green directions. So right now, if you can obtain the relation between the relieved stress and the displacement, then you can determine the stress. Okay. it will be a little bit compressed, but the delta D theta will be the displacement in this direction, and in this direction. So the theta will be different for these three lines. Okay. So the displacement after you relieve the stress, the displacement will be function of the stress you made. Okay? If this measurement is nearby the tunnel wall, very close to the tunnel wall, then you will measure this, and this. Like I introduced you for the surface relief. Okay? So if you can determine this and you assume this equals to 0, you have this, you have this, you have this, and you have this. And if you have a two isolated location, then you can obtain the stress tensor, the components of stress tensor in global coordinate system, like I showed you. Okay. So the function there will be the function of theta and elastic constant, because it will be the relation between displacement and the stress. So you should have some elastic constant involved. Then how to get those elastic constants? When you drill in this borehole, you must have some rock holes. So you will have the rock here. You can do in the experiments to obtain the elastic constant for the rocks where you measure in situ stress. So those elastic constant you will try to use the rock hole when you drill in the borehole. Okay. So like I mentioned to you before, if this measurement is very near the borehole, then you assume the sigma y prime equals to 0. If this is not really close to the tunnel wall, it will be a little bit away from the tunnel wall, then if you assume a sigma y prime, then this will be not unknown, it will be a known variable. Then you still have the 6th equation to determine the 6 unknowns. So the procedure will be the same. You have a measurement here and you have a measurement here. Then you can solve the stress components in the global coordinate system. I think this will be the most complex one, and I will not give you any equation because it will be very complex. This cell, we call it the CSIRO triaxial strength cell, which is developed by an organization in Australia. CSIRO will be a research institute in Australia. So they developed this. So you will have a device or a gauges like this. You will have a device like this. Okay? And you will have a strength of set in here, in here, and in here. You know, strength of set will have 3 strain gauges. So here you will have 3 gauges. Here you will have 3 strain gauges. Here you will have 3 strain gauges. So you will have 2 coordinate system, global coordinate system. You have a device like this. You have a strain gauge here, strain gauge here, and strain gauge here. So you will have, I don't remember it will be theta. Yes, it will be theta. So you will have a strain rosette here. Theta may be equals to, if this will be 0, 90, 118, 270, and this could be 320, something like that. Okay, so you will have the first strand of sand here, and you will have a strand of sand here. The theta could be equals to like 70 or something, and you will have another. So in this direction, we define it as theta. In this direction, in this direction, in this direction, we call it a theta. Okay, you have a H like this, then you will have the strand of set at a different theta. And you will have the strand of set. So you will have a strand of set in different directions. Then you will have omega. Can you understand? As I showed you, when you have the strand of set like this, if you want to determine the stress in this coordinate system, then you will have epsilon A, epsilon B, and epsilon C. And you can determine the sigma x and the sigma y and the tau xy. Epsilon x, epsilon y, and the gamma xy. You can determine this from this and this. During the calculation, you need to have the theta, right? So right now the theta will be the omega. So the strain, here you have a strain theta and omega. You have a 3 theta, you have a 3 omega. So you will have a 9 measurements for the strain. Okay? And the strain at a single point around a tunnel at any single point will be the function of the elastic constant and the stress at the local coordinates. Okay? So you will have the local coordinate system, sigma x prime, sigma y prime, sigma z prime, tau x prime z prime, tau x prime y prime, tau y prime z prime. You will have 6 variables to be determined. Okay? So you can have a 9 measurement, and you will have only 6 variables. You can determine the unknowns, and you will have 1 redundant. You will have 3 redundant equations. To make your back calculation can be optimized. Fit the 9, best fit the 9 equations. Okay? And this will be the local coordinate system. You need to remember. If you need to doing the stress concentration correction, you need to calculate it. Okay? You need to understand at that location what is the stress concentration, and you measure low stress will be the results of stress concentration. You need to make a modification. Another possibility is you trying to drilling a borehole away from the tunnel wall, saves 5 times of the radius or 2.5 times of the diameter of your tunnel wall. Then the stress concentration will be minimized. So you can drilling a borehole to a distance which is not influenced by the stress concentration. Then you will have your coordinate system, and you measure this 6 variable which is not influenced by the excavation of the tunnel. And you know the coordinate system which you want to obtain. For example, you have a coordinate system like this, okay? And you can determine the 6 variables in this coordinate system. And what coordinate system you want to have? you want to have the coordinate system like north, south, east, west, and vertical. So to determine this coordinate system, you have the stress tensor. Then you can rotate to these directions. Okay, so this will be a solution for overcome the stress concentration and the disturbance around the carbon. This will be a very good strategy to overcome it. The procedure will be the same. You drill in a small borehole, a larger borehole first. Like this, you drill in a large borehole. And then you drill a small borehole. And you try to insert this gauge to this location. And trying to expand it. And trying to make this strain gauge attached to the surrounding rock. And then you will overcoil it. And the stress will be relieved. And those strain gauge will give you some readings here. Then you can solve the stress case. Okay? I think it's about the things I like to mention to you. But I will not ask you to write this homework. It will be good news. Okay, I will stop here.